Math 2414, Taylor and Maclaurin series, video 7, Maclaurin series for sine of x, proof of convergence. In the previous video, we found a Taylor series for e to the x centered at x equals 2, but we did not prove that the series actually converged to the desired function by using Taylor's formula and Taylor's theorem. We're going to do that in this video, but just a reminder of the things that we have at our disposal and what we're going to do to show convergence. In the upper left corner, of course, is the generic Taylor series for a function, where if you have a function that's differentiable as many times as you want, then we can build a Taylor series using this formula. Below that is the formula for the Taylor polynomial, where we take the sum and we stop it at some upper limit k. So basically, it's a finite polynomial to approximate our function. And then below that is the definition of the kth remainder, where we take the function and subtract the kth Taylor polynomial. Basically, it's the tail end of the Taylor series, so to speak. Taylor's formula says, that we can estimate the remainder, not estimate it, but that the remainder is equal to a certain expression. Namely, the kth remainder is equal to the k plus first term from the Taylor series, but not evaluated to the center, but instead evaluated at some number z, if I can get this thing to draw, hold on folks, but rather evaluated at some number z, where that z is between the center and whatever x you put into the function at the time. And by representing the remainder as a single term, instead of this difference, which would be a function minus an infinite number of terms, we can take advantage of Taylor's theorem, which says if the limit as k approaches infinity of the kth remainder is equal to 0, then the Taylor polynomials do approach the original function on some interval centered at, well, the center. So finding the series is going to be pretty easy, and showing that it converges to sine of x will also actually be pretty easy. You just have to get accustomed to how these things look. All right, so let's start by finding the Taylor series, actually the Maclaurin series, so the Taylor series centered at x equals 0. So we're going to find the sum from n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial times x to the n. And again, the hardest part about building these series, whether it's a Taylor series or a Maclaurin series, is figuring out what all the derivatives look like. Now, luckily, our function is just sine of x, and its derivatives are fairly predictable. So we're going to make a table. We're going to make a table where we have our n. So n will start at 0. Our derivative evaluated at 0. And then finally the term. So let's label these columns. N, nth derivative, before we do anything to it, nth derivative evaluated at 0, and then finally what our term's going to look like in the series. All right, so let's just start with 0. Remember, our function was sine of x. Actually, I don't think I ever wrote that anywhere. We're finding the Taylor series, or the Maclaurin series, the Taylor series centered at 0 for sine of x. So our original function is sine of x. And if we evaluate sine of 0, we get 0. Well, that's convenient. So our first term is 0 because it kills everything. When n equals 1, the derivative of sine is cosine. 1 second. There was a big break between the first 5 videos and the ones 6 onward. And for some reason in my mind, I was thinking we've already done the power series for sine of x, but I'm not seeing it. So, guess not. All right, so anyway, when n equals 1, our first derivative is cosine. Cosine evaluated at 0 is 1. So our term won't disappear. We'll have 1 over 1 factorial times x to the first, but that's just equal to x. All right, so there's our first non-zero term. When n equals 2, our next derivative, the second derivative, if you will, the derivative of cosine is negative sine of x. But when we evaluate that at 0, we get 0. So that term's gone. And if you think about it, every other derivative will be either sine or negative of sine. And so when we evaluate it at the center, we'll get 0, so that'll kill the term. So it looks like every time our n is even, our derivative will either be sine or negative sine. When we get to the fourth derivative, it'll be sine, which will give us a 0 for the derivative evaluated at 0, which will eliminate that term. So that being said, I think we can skip all the even powers in this case, or all the even derivatives, because it will give us 0. So let's get right to the third derivative. The derivative of negative sine of x is negative cosine of x. And when we evaluate that at 0, we get -1. And so our next term, our third term, or at least the second one that doesn't disappear, is -1 over 3 factorial x cubed. And we'll just leave it like that for now. I know I could write it as -1/6 x cubed. We could put in 4, but the next derivative is going to be sine, and that's going to vanish at 0 at the center, so we don't need to mess with it. We'll skip right to the fifth. Remember, the fourth derivative was sine. Oh, wait a second. We're just going to start repeating derivatives. Derivative sine is cosine. The fifth derivative evaluated at 0 is 1. And so we have +1 over 5 factorial x to the fifth. The sixth derivative would be negative sine, which would disappear when we put in 0. So the seventh derivative will be negative cosine. And by the way, if skipping the even ends is messing with you, then don't skip them. Write them down so that you can see them. But you'll quickly notice that all the even ends 0 out, and all the odd ones oscillate between 1 and -1. We're going to make an alternating series. -1 over 7 factorial x to the seventh. So it seems like our series is x minus 1 over 3 factorial x to the third, plus 1 over 5 factorial x to the fifth. Give me 1 second to see if I can grab this whole table and move it over some. Select all of you. And let's just see if I can grab you and move you over a little bit. There we go. There we go. All right. So where were we? We were at +1/5, 1 over 5 factorial x to the fifth, minus 1 over 7 factorial x to the seventh, plus ... So if we were to write out this series, it would look something like that. But if we wanted to write it in sigma form with the sum, we really shouldn't start at n equals 0, because we would be saying that we're going through all the powers of x, and we're not. We really shouldn't say x to the n, I should say, because if we did, we're going through all the powers, even the even ones, which disappear. When clearly the odd powers are making a nice little pattern. We have an alternating series. We have odd powers and odd factorials in the denominators. If you'll recall, we can write an odd number as 2n plus 1. So it looks like our series is going to be -1 to the n over 2n plus 1 factorial x to the 2n plus 1. And you can check it if you're not sure if you should write 2n plus 1 or 2n minus 1, both of which represent generic odd numbers. But if we put in 0, we should get our first term, which was just x. We put in 0 here, we get 1 factorial. We put 0 here, we get x to the first power. And if we put 0 here, we get -1 to the 0 power, which is 1. So we get 1 over 1 times x. We have our alternator set up correctly. We have our odd numbers starting out correctly. This is a series you should memorize. This is a series you should memorize. Whether you memorize it in sigma form or just remember it as x over 1 minus 3 factorial x cubed plus 1 over 5 factorial x to the fifth, and so on and so on. So this will be a series you need to know moving forward into other math, engineering, and physics classes. Now, we haven't checked convergence. This should converge for all real numbers. And I want to clarify, this is not what I was saying at the beginning when I said we were going to check for convergence or proof of convergence right here. We have actually 2 things we need to do. Where does the series converge? And does the series converge to sine of x? We're going to prove that also. All right, so let's start by asking, where does the series converge? Where does the series converge? Now remember, to answer the question, where does the series converge? In other words, for what values of x will this infinitely long polynomial converge? Got a blank page in here somehow. We use the ratio test. So if we set up our limit for our ratio, L equals the limit as n approaches infinity. It might help if we actually see what our series is. So let's write it up here. Sum equals 0 to infinity, 1 over, excuse me, not 1, but negative 1 to the nth power over 2n plus 1 factorial x to the 2n plus 1. But if we were to do the ratio test, we would start with the next term, which would be negative 1 to the n plus 1 over 2 times the quantity n plus 1 factorial times x to the 2 times the quantity n plus 1 plus 1. And it is important to write it like that because we're replacing each of these n's with an n plus 1. Sorry, the line width got a little skinny there. Got some formatting issues here. Let me fix them. But when we replace the n with an n plus 1, because it has a 2 in front of it, we have to reuse parentheses to make sure the 2 gets multiplied across the entire n plus 1. But that's just the next term, and now we have to divide it by the current term, but dividing it by the current term means multiplying times the reciprocal of the current term. So we have to take our expression up here and multiply down here by the reciprocal. So that will put 2n plus 1 factorial on top, negative 1 to the n, x to the 2n plus 1 on the bottom. All right, so it's a messy setup, but it's legit nonetheless. One thing we should probably do is clean up the 2 times n plus 1 plus 1s everywhere. In other words, this and this, we need to distribute the 2 in combined like terms, but that's not that difficult to do. We'll get 2n plus 2 plus 1. And when we do 2n plus 2 plus 1, we just get 2n plus 3. 2n plus 3. And we'll get the same thing up there in the exponent on the x. Make that x a little better. Okay, now we're ready to do some canceling. I'm not going to worry about the alternators because they're inside an absolute value, and of course, the absolute value of 1 or negative 1 is equal to 1. So we can just cross them out because they won't have any impact on the rest of it. As far as the x's, we can subtract exponents. 2n plus 3 minus 2n plus 1 will give us just 2. So these x's cancel all of those and leave an x squared. But what about the factorials? What do you get when you have 2n plus 1 factorial over 2n plus 3 factorial? If you're not sure, write it out. But if you're going to write it out with the hopes of canceling something, always start with the larger of the two. If we start with 2n plus 3 factorial, it would be 2n plus 3 times the next number 1 less than that. What's 1 less than 2n plus 3? 2n plus 2. What's 1 less than that? 2n plus 1. And at that point, I don't need a plus there. We'll take it all the way down to 3, 2, 1. What's the top one? Well, it starts with 2n plus 2. Excuse me, it starts with 2n plus 1. And it goes all the way down to 3, 2, and 1. You know why I didn't write the second one on that one and just jumped right to 3, 2, 1? Because I saw that this thing would cancel with all that, and I don't need to mess with it. Hold on, folks. All this cancels all that. And so we are left with just 1 over 2n plus 3 and 2n plus 2. So that's what's going to happen in the factorials. All right, let's get rid of all that and just cross it out up here. Okay, so this factorial will wipe out all but the first 2 factors in this one. All right, well, so let's see what we have left in this mess. We have the limit as n approaches infinity the absolute value. The only thing we have on top is x squared. And on the bottom, we have the two remaining factors from when we canceled the factorials. Okay. Now, we've seen this game before. The x squareds cancel. What am I talking about? The x squared is independent of the n, which means we can pull it out of the limit. And we're left with the absolute value of 1 over 2n plus 3 times 2n plus 2. But this is an old story. Because the denominator is going to infinity, this whole fraction is going to 0. And so we get the absolute value of x squared times 0, which of course is equal to 0. Our limit is equal to 0. And what does that mean about convergence? Well, in the ratio test, when the limit of that ratio is less than 1, 0 is less than 1, we get convergence. And since this was independent of the value of x, we can conclude, therefore, that the series converges for all x. Converges for all x, an element of negative infinity to infinity. If you're wondering what's up with this symbol, I invite you to go back and watch the previous video, but in short, it's a symbol for the phrase for all, or equivalently for every. So series converges for all x's, an element of that interval. All right, so we found the series. We know that's, not sure what happened there. We know that sine of x is equal to the sum from n equals 0 to infinity, negative 1 to the n, over 2n plus 1 factorial, x to the 2n plus 1. And it converges for all x's on the whole number line. The only other thing I want to do, and this is kind of pushing the envelope a little bit for some Calculus 2 classes, but I like pushing envelopes, is I want to show that the series actually does converge to sine of x. We know it converges. Now I just want to convince you that it converges to sine of x. And we're going to do that by using Taylor's formula. So we will have a formula or a closed expression to represent the remainder. And Taylor's theorem, we're going to take the limit of that remainder and get 0, which shows us that the partial sums of the Taylor polynomials converge to the actual series. Excuse me, the Taylor polynomials converge to the actual function. All right, so let's start with Taylor's formula for the, let's start with Taylor's formula for the remainder. Excuse me, Taylor's formula for the remainder says that the remainder is going to be equal to the next term in the Taylor series, so the k plus first derivative, evaluated at some number z over k plus 1 factorial times x minus the center, which is just x because the center is 0, to the k plus 1 power for some z between the center, but it's a Maclaurin series, so its center is 0, and x. So how are we going to do this? Well, unlike the previous video where all the derivatives were e to the x, the derivatives here aren't the same. But we can summarize the derivatives, that the derivative, it doesn't matter what you put for the order of the derivative was always one of 4 things. 1 second, folks, we're going to pause this. Had quite a big gap between when I just paused and now, so I'll try to pick up exactly where I left off or reasonably close. We were in the process of coming up with an expression for the remainder, and we're going to show that the remainder approaches 0, but in order to do that, we need an expression for the derivative. I do remember saying that unlike the previous example where all the derivatives were the same, they were all e to the x. That's not the case here, but we do know that the derivative has to be one of 4 things. The derivative has to either be sine, the original function, cosine, the derivative, negative sine, take a derivative again, or negative cosine, and then it repeats. So although we don't know the derivative, we know that it has to be one of these 4 things. Now, luckily, both sine and cosine have a range between 1 and negative 1. So one thing that we can definitely say about this derivative is that no matter what derivative we take and no matter what we put into it, its value will always be between -1 and 1. And that looks like we're going to set up the squeeze theorem or the sandwich theorem if we can just build this up to look a little bit more like our remainder. So let's take our remainder and, let's take this inequality that we have down here, this one at the bottom that I'm about to highlight, and let's see if we can incorporate that somehow into our remainder, or incorporate our remainder into that. All right, so we have the kth derivative evaluated at any number of our choice is going to be between -1 and 1. We can, and it doesn't matter what derivative we take, so let's go ahead and replace the k with the k plus 1, because this is true for all derivatives, even this one. And dividing everything by k plus 1 factorial is not going to change the direction of the inequality, because all those factorials are positive. Now, our z, excuse me, has to be between 0 and x. And we are talking about z, so we'll replace the x inside the derivative with a z, because the inequality is true for any value, so we'll use z. And we also need to put the x to the k plus 1. Now, the x is either positive or negative, or rather x to the k plus 1 is either positive or negative. If it's positive, then we could just multiply everything by x to the k plus 1. Really squeezing things in there. Let's not do that. Let's just rewrite it. Negative x to the k plus 1 over k plus 1 factorial is less than or equal to the k plus 1 derivative evaluated at z times x to the k plus 1 over k plus 1 factorial, which is less than or equal to x to the k plus 1 over k plus 1 factorial. Now, this is if the x to the k plus 1 is positive. If it's 0, then everything's equal because everything becomes 0. But if it's negative, then it would actually reverse these inequalities, but it's not going to change the net result because the end limits are going to end up being 0 anyway. We'll just squeeze it in reverse. All right. So now we have to take the limits of the expressions on the left and right ends of the double inequality. So we need to take this limit and this limit. And if you'll notice, these expressions are the same, except that one is the opposite of the other. So once we know the limit of one, we know the limit of the other. So let's take the limit of the one without the negative. The limit is k approaches infinity of x to the k plus 1 over k plus 1 factorial. Well, we've seen this type of limit before. We saw it slightly differently before. I think it looked like this. The limit is n approaches infinity of x to the n over n factorial. But we saw that limit before and it was equal to 1. Is this the same limit? It is. And the reason it's the same limit is because we can do a change of variable. We can say that n is equal to k plus 1, which would put a k plus 1 here and here. And as n approaches infinity, as n approaches infinity, k approaches infinity, because we would just subtract 1 from n to get k. Infinity minus 1 is infinity. So these two limits are exactly the same, or they're going to equal each other. With a little bit of change of variable, we can see that pretty straightforward. Excuse me. So we have that limit is equal to 0. Well, that means that this limit goes to 0, and this goes to the opposite of that limit, so it's still 0, which means the guy in the middle goes to 0. And remember, the guy in the middle was the kth remainder. And so we can conclude that the limit as k approaches infinity of the kth remainder is equal to 0, and therefore the series converges to sine of x. Now, some of you may be wondering, do we really have to do all this stuff that we just did? And the answer is both yes and no. Technically, yes, because when you calculate a Taylor series, really what we're saying is if a function has a series representation, then that Taylor series is the correct representation if a function can be represented with the power series. Not all functions actually can. And the functions that can't be represented by their Taylor series exist. We're not going to get into them now. If you take a more advanced calculus class or an analysis class, you'll see classes of functions whose Taylor series do not converge to the actual function. So is it something that needs to be done? At this point in this game, not really, I'm just demonstrating it. But in the long term, yeah, it does. If you take anything away from this rather long video, which is actually take 3, it should be what's in the box in the lower right corner, lower left corner. That sine of x is equal to that sum, either as a polynomial or in sigma notation.